let's look at ratios. We've already seen how to determine the convergence of a geometric series. For example, does the series the sum n goes from 1 to infinity of 1 over 4 to the n converge or diverge? Well, this series converges, right, by which test? By the geometric series test, if you like, because the common ratio, right, this common ratio between the terms is 1/4, and that's less than 1. What if we modify the series somewhat? So what if instead of looking at this series, we looked at the series, the sum n goes from 1 to infinity, not of 1 over 4 to the n, but say n to the 5th over 4 to the n. That series is not a geometric series anymore, but it ends up at least approximately looking like one. Let me just give some names to these things. Let's say that a sub n is n to the 5th over 4 to the n. And what I'm trying to determine is the sum n goes from 1 to infinity of a sub n. Well, I'm probably not going to actually determine this value, right? But I'm just trying to answer the question of whether or not that series converges or diverges. Now, if I plug in really big values for n, I can get a sense of what these terms look like, right? A sub 1,000 is, well, hard to write down, but I can at least write down 1,000 to the 5th over 4 to the 1,000th power. And it's hard maybe to see what that number looks like. A sub 1,001, right, the 1,001st term is 1,001 to the 5th over 4 to the 1,001st power. And what's the ratio between these terms, right? How big are these terms compared to each other? Now, if this were actually a geometric series, right, the ratio between subsequent terms would be the same. And this isn't a geometric series, but let's see if we're close. So a sub 1,001 divided by a sub 1,000, well, a sub 1,001 is 1,001 to the 5th power over 4 to the 1,001st power, divided by a sub 1,000, which is 1,000 to the 5th power, divided by 4 to the 1,000th power. I could rewrite this, right, because I've got a fraction with fractions in the numerator and denominator. I could rewrite this as 1,001 to the 5th times 4 to the 1,000th power, divided by 1,000 to the 5th times, and the denominator and the numerator, I can write that in the denominator, is 4 to the 1,001st power. Now I should split this up and think about these two pieces separately, right? How big are these two pieces? Well, 1,001 to the 5th power divided by 1,000 to the 5th power, this piece here is pretty close to 1. And this piece here is, well, it's exactly 1/4. So if I've got a number that's close to 1 and I'm multiplying it by a number that's close to 1/4, this fraction is, well, it's not equal to, but it's about 1/4. And if you think about it, there's nothing special about 1,000 here, except that it's really big. So the ratio between subsequent terms, at least if those terms are far enough out in the sequence, that ratio is close to 1/4. Can I make this precise? I'll use a limit. What I'm saying is that the limit as n approaches infinity of a sub n plus 1 over a sub n, in this case, is equal to 1/4. That if I choose n big enough, I can make that ratio close. How close? As close as you want to 1/4. I can be very explicit in this case. Right? I could pick an explicit value of epsilon. Let's just pick 0.1. And then it turns out that whenever little n is bigger than 15, a sub n plus 1 over a sub n is in fact within epsilon of my limiting value of 1/4. And in particular, if a sub n plus 1 over a sub n is within 0.1 of 1/4, well, that also means that a sub n plus 1 over a sub n is less than 1/4 plus 0.1. And that's enough to set up a comparison with a geometric series. I could multiply this inequality by the positive number a sub n, and I'd find out that a sub n plus 1 is less than 1/4 plus 0.1 times a sub n. Well, this also means that a sub n plus 2 is less than a quarter plus 0.1 times a sub n plus 1. But a sub n plus 1 is less than a quarter plus 0.1 of a sub n. So a sub n plus 2 is less than a quarter plus 0.1 squared times a sub n. Now, this fact with n replaced by n plus 2 tells me that a sub n plus 3 is less than a quarter plus 0.1 times a sub n plus 2. But a sub n plus 2 is less than a quarter plus 0.1 squared times a sub n, so a sub n plus 3 is less than a quarter plus 0.1 cubed times a sub n. Well, this works in general, right? What I'm really showing here is what? I'm showing that a sub n plus k is less than a quarter plus 0.1 to the kth power times a sub n. And this is true whenever n is at least 15. So in particular, I'm showing that a sub 15 plus k is less than a quarter plus 0.1 to the kth power times a sub 15. The key point here is that a quarter plus epsilon is still less than 1. Well, the series that we're interested in is the sum n goes from 1 to infinity of a sub n. And that series converges precisely when the series n goes from 15 to infinity of a sub n converges. The first 14 terms here that aren't included there don't affect convergence at all, right? That's just adding 14 more numbers to this. But now how do we analyze this? Well, here's the deal, right? I've got a bound on the size of these a sub n's as long as n is at least 15. I've got this. So the sum n goes from 15 to infinity of a sub n is equal to the sum k goes from 0 to infinity of a sub 15 plus k. Right? The 0 term here is just a sub 15, which is exactly the same as the first term here. K equals 1 is a sub 16 here, and that's exactly the next term here. So these are really the same series. But now what do I know about this series? Well, that series converges. Why? Because the sum k goes from 0 to infinity of a quarter plus 0.1 to the k times a sub 15 converges. Why does this series' convergence affect this series' convergence? Well, this series' terms are bigger than this series' terms, and this series' terms are all positive. So this follows from the comparison test, that if this series converges, then this series converges. But now why does this series converge? Well, this series converges by, say, the geometric series test. And how does the geometric series test affect this? Well, this is a geometric series. This a sub 15 is just a constant, and the common ratio is a quarter plus 0.1, and a quarter plus 0.1 is less than 1. So the common ratio being less than 1 means that this geometric series converges, means that this series converges, means that the original series that we're studying converges. This is a specific case of a very general procedure that I'm studying the convergence of some series. The sum n goes from 1 to infinity of a sub n. Right? I want to know if that converges or diverges. And let's suppose that all the terms in the sequence a sub n are positive. Well, what I'm suggesting that we should try to do is to look at the limit as n approaches infinity of a sub n plus 1 over a sub n. Right? This series is almost surely not a geometric series. Right? Most series aren't geometric series. But I could try to see, is it close to a geometric series? What is the ratio between subsequent terms? Is it close to anything eventually? Right? That's what the limit's asking me. So let's suppose that this limit does exist. Let's suppose that this limit equals L, and let's suppose that L is less than 1. Well, then what I'm suggesting is that we pick some small epsilon. How small? Well, I want epsilon so small that L plus epsilon is less than 1. If L is less than 1, I can definitely pick epsilon small enough so that even if I add epsilon to L, I'm still less than 1. Now I'm going to use epsilon in this limit, right? The fact that this limit equals L means that there's some big N, let's just say find big N, so that whenever little n is bigger than or equal to big N, a sub n plus 1 over a sub n should be within epsilon of L. And in particular, this should be less than L plus epsilon. And why does that help? Well, this inequality implies that A sub big N plus little k is less than L plus epsilon to little k times A sub big N. Where does this come from? Well, it really does come from just applying this a ton of times. What this is saying is that as long as n is at least big N, then the ratio between subsequent terms is less than this factor. And that means that I can overestimate the big N plus kth term by this factor to the kth power times just whatever the big nth term is. Now, how do I use this? Well, the sum k goes from 0 to infinity of this, of L plus epsilon to the k times A sub n, converges. And why is that? Well, this is a geometric series with common ratio L plus epsilon, but that common ratio is less than 1. Right? That's exactly why I picked epsilon so small up here. So I've got a geometric series with common ratio less than 1, so this series converges. But then, by the comparison test, I know something about this series. I know that the series little n equals big N to infinity of A sub n also converges, because these terms are all overestimated by these terms. And consequently, the original series, the sum n goes from 1 to infinity of A sub n, also converges, because I can get this from this just by adding on finitely many extra terms. We can summarize this. So here's a statement of what's normally called the ratio test. And it goes like this. I want to know whether the series n goes from 1 to infinity of A sub n converges or diverges. And I'm only going to study series, the terms of which are all positive. And I need that because my argument was using the comparison test, and the comparison test requires series with at least non-negative terms. All right, then I'm going to look at the limit n goes to infinity of A sub n plus 1 over A sub n, the limit of the ratio of subsequent terms. Let's suppose that that limit exists and equals L. Then there's three possibilities. If that limit is less than 1, then this series converges. And it's converging because I can do a comparison test between this series and a convergent geometric series. If that limit is bigger than 1, then this series diverges. And I know that because, again, if this limit is bigger than 1, I can compare maybe not the whole series, but at least after a while, for past some big nth term, I can compare this series to a divergent geometric series. And then finally, maybe L is equal to 1, and in that case, the ratio test is silent. It doesn't tell us any information either way.